Last class, we discussed free electron gas in one dimension. Here we are going to discuss free electron gas in three dimension. Okay. So, the electrons are confined. Here we are considering electrons are confined in a cube of edge length L. Okay. And outside, if electrons are confined in this cube, the outside wave function psi is equal to 0. And inside psi is not equal to 0, there is a wave function, and outside psi is equal to 0. Okay, and the cube of side edge length L means outside this cube psi is equal to 0, and inside this is not equal to 0. So we will get a boundary condition at the boundary L. Okay, this is a Schrodinger equation for 3-dimension free electron gas. Minus h bar square over 2m dou square over dou x square plus dou square over dou y square plus dou square over dou z square psi k of r is equal to ek psi k of r. Okay, this is Schrodinger equation, and the potential inside is equal to 0, and outside we are considering this as infinity. So our Schrodinger equation becomes like this. Okay, and the solution for this Schrodinger equation, if it's confined in a cube of length, edge length L, psi n of r is equal to a sine nx pi x over L sine ny pi y over L sine nz pi z over L. This is the solution for this wave equation. This is the equation of a standing wave. But it's more convenient to introduce a wave function which satisfies periodic boundary conditions, because we are considering lattice points like this. If it's in one dimension, we are considering lattice points like this, and we need a wave function which shows similar character at similar periodic positions. Okay, if this is the one-dimensional lattice, if the wave function psi n here should be equal to the wave function psi n here, because the surroundings of this lattice points are similar, so the wave function here at this point should be equal to the wave function at this point. Okay, so that's why we are introducing a wave function. We are taking a wave function which satisfy boundary conditions. Okay, that wave function, let us take psi k of r equal to e raised to I k dot r. Okay, this wave function satisfies periodic boundary conditions, and psi k of r equal to e raised to I k of k dot r. This is equation 2. Okay, so this I can write. This is the equation of a traveling wave. This wave function is similar to the equation of a traveling wave. So the wave vector k is equal to kx x cap plus ky y cap plus kz z cap. Okay, and the position vector r is equal to x cap plus y cap plus z cap, and we will get k dot r is equal to kx x plus ky y plus kz z. Okay, so the wave function psi k of r is equal to e raised to I kx x plus ky y plus kz z. Okay, this is the wave function. This is a form of wave function, form of traveling wave, equation of a traveling wave, and we got the wave function like this. And our condition is the wave function should be periodic in nature. Wave function should be periodic in nature with a length L. That means this equation, for example, I can write psi k of x. In x direction, the wave function is equal to e raised to I kx x. Okay, so in that x direction, the wave function at the position x should be equal to the wave function at the position x plus L. Okay, this lattice has a period L. That's why I am considering the wave function at the point x is equal to the wave function at the point x plus L. So here the wave function at the point x is e raised to I kx into x. That should be equal to e raised to I kx into x plus L. Okay. So e raised to I kx x is equal to e raised to I kx x plus L means e raised to I kx x into e raised to I kx L. Okay. This equation means e raised to I kx x is equal to e raised to I kx x into e raised to I kx L means e raised to I kx L should be equal to 1. Okay. If e raised to I kx L is equal to 1, that means cos kx L plus I sin kx L is equal to 1, and this is the imaginary portion that should be equal to 0 because RHS contain only real portion. So cos kx L is equal to 1 means kx L is equal to n into 2 pi, where n is equal to 0, 1, 2, 3, etc. Okay, or plus or minus n 2 pi. Okay. From that equation we will get kx is equal to n into 2 pi over L. Okay, kx equal to n into 2 pi over L, where n is equal to 0, 1, 2, 3, etc. Plus or minus n 2 pi over L. Okay, in the similar manner we will get ky is equal to plus or minus n into 2 pi over L, as well as kz equal to plus or minus n into 2 pi over L. Okay, so we got the value of wave vector in different directions. The values of wave vector in different directions. If we substitute equation 2 in equation 1, we will get minus h bar square over 2m dou square over dou x square plus dou square over dou y square plus dou square over dou z square of e raised to I k dot r is equal to e raised to I k dot r. Okay, and that is equal to minus h bar square over 2m, and we know dou square by dou x square of e raised to I k dot r means e raised to I into kx x plus ky y plus kz z plus dou square by dou y square, the same thing, e raised to I kx x plus ky y plus kz z plus dou square by dou z square e raised to I kx x plus ky y plus kz z, and that is equal to ek into e raised to I kx x plus ky y plus kz z. Okay, and so we can differentiate it minus h bar square over 2m. If we differentiate this twice, we will get e raised to I kx x plus ky y plus kz z into, we are differentiating twice with respect to x, so we will get ikx all square. Okay, plus e raised to the similar thing into iky whole square plus e raised to the similar thing into ikz whole square is equal to ek into e raised to I, the similar thing. Okay, e raised to ikxx plus kyy plus kz. Okay, so and we can take this outside, that is minus h bar square over 2m into e raised to I kxx plus ky y plus kz z into minus ikx square. That means minus I square is minus 1 minus k x square minus k here minus k y square minus k z square is equal to ek into e raised to I into kxx plus ky y plus kz z. Okay, so this both will get cancelled, and we will get ek is equal to h bar square over 2m into kx square plus ky square plus kz square. This is the wave vector square of the wave vector k, that is equal to h bar square over 2m into k square. So ek equal to the occupied orbitals can be represented as the points inside the sphere in k space. Okay, this is the sphere in k space in momentum space. So the in that system of n electron, the occupied orbitals in the ground level, the occupied orbitals can be represented as the points inside the sphere in k space. Okay, with that the radius of that sphere is kf, the energy at the surface is ef. So ek equal to h bar square 2m over k square, and this is the Fermi energy at the surface is equal to F is equal to h bar square over 2m kf square. Okay, so this is the Fermi energy, and in 3 dimension the system of this we are considering the system of n electrons in 3 dimension, and in the momentum space the occupied orbitals of the system of n electrons can be represented as the points inside the sphere in k space or in momentum space, and with the sphere with radius kf and the energy at the surface is ef, is the Fermi energy. Ef is equal to h bar square over 2m kf square. Okay, actually in one dimension we have represented the energy levels like this, n1, n2, and nf is the topmost level in ground state, and this is the Fermi energy ef, and in one dimension we have represented like this, and in 3 dimension we are considering free electron gas in 3 dimension, and we are taking this in momentum space. So instead of this energy levels we are considering the energy, we are considering the orbitals. Here we have represented the orbitals like this, and in 3-dimensional space we are considering the orbitals are inside a sphere in the momentum space, with that the radius of that sphere is kf and the energy at the surface is ef, Fermi energy. Ef is equal to h bar square over 2m kf square. Okay, we used to represent energy levels in one dimension like this: E1, E2, E3, etc. Okay, and in ground state till Ef, and energy levels like that. In ground state, 2 electrons occupied in each energy level with opposite spins. Okay, for each energy level there is a specific k value, there is a particular k value for each energy level. That means for a specific k value there corresponds 2 electrons or 2 number of orbitals. Okay, if we consider 3-dimensional case, the periodicity of wave function gives the value for kx is equal to 0 plus or minus 2 pi over L plus or minus 4 pi over L, etc. and ky is equal to 0 plus or minus 2 pi over L plus or minus 4 pi over L, etc. As well as kz is equal to 0 plus or minus 2 pi over L plus or minus 4 pi over L, etc. Okay. And if we take kx axis, this is kx, we get the values 0, 2 pi over L, 4 pi over L, 6 pi over L, etc. And in the left side minus 2 pi over L, minus 4 pi over L, etc. Okay, the difference between the values of kx is 2 pi over L. That means in the length of 2 pi over L, there corresponds a kx value. There is a kx value in each length of 2 pi over L. Okay, in the similar manner ky and kz also. That means in three dimension, if we consider a volume of 2 pi over L whole cube, there corresponds a particular k value. That means in this sphere, if we consider a volume of 2 pi over L whole cube, there corresponds a particular k value. That means we need to consider the number of electrons or number of orbitals in this sphere. In a way, the total volume of this sphere is 4 by 3 pi kf cube. And for each k value, there is a volume of 2 pi over L whole cube. That means in this volume of 2 pi L whole cube, there corresponds a k value. So we will get the number of k values in this net volume, and each k value corresponds to 2 electrons with the opposite spins. That means we get the number of electrons. Number of electrons is equal to 2 into 4 by 3 pi kf cube over 2 pi L whole cube. Okay, so we will get 2 into 4, 8 and 2 cube, that will get cancelled. And we will get, this implies this is 1 by 3 L cube, L cube, kf cube over pi square is the number of electrons or number of orbitals. Okay, this is L cube, cube of the length, and that is the volume in real space. So we can write the number of electrons is equal to inside the sphere is equal to Vkf cube over 3 pi square. Okay, this is the number of electrons inside the volume of this sphere. Okay, so we need to find out the value of kf. We need to find out the value of kf from this equation. Kf cube is equal to 3 pi square n over v, and kf is equal to 3 pi square n over v whole raised to 1 by 3. Okay, this is the value of kf, and the Fermi energy EF is equal to h bar square over 2m into kf square. Kf square is 3 pi square n over v whole raised to 1 by 3. Whole square means whole raised to 2 by 3. So this is the value of kf. And this is the value of EF, is the Fermi energy in terms of number of electrons per unit volume. Okay. And next we need to find out the electron velocity. And that electron velocity is electron velocity is, actually the momentum is mass into velocity. Mass into velocity is h cross kf. Mass into velocity, h cross k is the momentum. So this is the mass into velocity. So Vf, the velocity, Fermi velocity, that means the velocity of electrons inside the metal is equal to, in ground state, is equal to h cross, the velocity of electron in the surface of the sphere is equal to Vf is equal to h cross kf over m. Okay, this is the velocity of electrons in the surface of this sphere. Okay. So let us discuss density of states, d of E. It is the number of orbitals per unit energy range. And we know the equation of Fermi energy F equal to h bar square over 2m 3 pi square n over b whole raised to 2 by 3. Okay. And if we consider the total number of orbitals of energy less than or is equal to E, generally we can write this equation as E is equal to h bar square over 2m 3 pi square n over b, 3 pi square n over b, n over b whole raised to 2 by 3. And from this equation we can write the number of orbitals of energy less than or is equal to E is equal to b by 3 pi square into 2m e over h bar square whole raised to 3 by 2. Okay, this is the number of orbitals of energy less than or is equal to E. And the density of states d of E is equal to the number of orbitals per unit energy range, and that is equal to V over 3 pi square 2m over h bar square whole raised to 3 by 2. We need to differentiate E, that is 3 by 2 e raised to 1 by 2. This is the density of states. That means the number of orbitals per unit energy range. Okay.